Hello guys, welcome to this video. In this video we will be continuing all our previous explorations about all the functions and developments that we did, and in this video we shall also find out more about the properties and all the different discoveries that we can make about this exact function and the distributions that we are studying. And meanwhile there would be a lot of solved problems as well, so just head forward to the video. We can start over from there. So today we are going to solve the following integral. Let me just write it down. This integral is as follows: I equals to 0 to 1, 0 to 1 fractional part of x by y dx dy. So this is the integral that we are going to solve today, and there would be a lot of concepts involved. So first of all we need to understand what does this second bracket means. So be cautious that this second bracket is not literally the same as a first bracket or something which is used to group items. So this second bracket right here means the fractional part. So what does a fractional part mean? The fractional part means that, let's say you have 1 by 2 inside it. So the fractional part will give you the answer of 1 by 2. Okay. Let's say you have 2.3. It will give you the answer 0.3. Okay. Let's say you have 5. It will give you the answer of 0. So what it gives you is basically fractional part of x is simply equals to x minus box of x, where box of x is the greatest integer less than equals to x, or the GIF function, right? So as for all of these examples, say for example 2.3, it is equals to 2.3 minus box of 2.3, and as we know the box of 2.3 is just 2, so it becomes 2.3 minus 2, which is 0.3. So it gives you the fractional part, and it is always positive. So what we do know is fractional part belongs in the interval 0 to 1. Well, fractional part can never be 1, so it can be only less than 1, but it can be 0. So this is basically the idea behind fractional part. Now the integral we are given is a rather peculiar one. So what we are seeing here is 0 to 1. Let us evaluate this simple integral first. So if we have 0 to 1 fractional part of x dx, now as I already told you, fractional part of x, so fractional part of x will equal x itself only when x belongs to 0 comma 1, because inside 0 comma 1 x is always a fraction, right? It's always less than 1. So that is why inside it always becomes x itself. So when the limit is 0 to 1 and you only have fractional part of x square, what you get is 0 to 1 x dx, which is basically 1 by 2. So this is one kind of an integral. Let us see another variant. Let us say we have I2 equals to 0 to 1 fractional part of x whole square dx. This would be again the same. This would be 0 to 1 x square dx, because we have a fractional part whole square not inside it. So that means fractional part of x is still x, and it will be 1 by 3. Now if you had something like this, where you have 0 to 1 fractional part of x cube dx, now this is a problem, because we will see that obviously fractional part of x becomes, we need to prove something here before we can jump to the conclusion, that we do know that fractional part of x is equals to x when x belongs to 0 to 1. But when x belongs from 0 to 1, we also know that x cube is also belonging to 0 comma 1, and that means fractional part of x cube should also equal x cube. This means this would equal 0 to 1 x cube dx, which is 1 by 4. So in a similar way we evaluate fractional parts, right? So now let us come back to the definite integral that we are interested in, which is a rather hard one, and we will do harder problems after this as well. I equals to 0 to 1 fractional part of x by y dx dy. Okay, and what we would like to do is we would like to understand how to solve this problem firstly, and secondly, how do we make sure that this problem has a closed form which we are interested in finding out. So firstly, what we are going to do is we are going to make a substitution. So we do not really like fractions, and we see that x by y is a perfect way to substitute something. So let u equals to x by y, where u is a new variable, and we are trying to keep y as a constant here because we are only interested in evaluating the inner integral. So x equals to uy is what we are going to substitute. So first of all, let us find out the new limits. U lower would just be x lower by y, which is 0, and then again u upper would just be u upper would be x upper by y, and x upper was 1, so this would be 1 by y, right? And differentiating, you get du should be equals to dx by dy because y is a constant here. So what our integral turns is as follows: 0 to 1, the 1 on the outside remains the same, and what we have inside is the lower limit becomes 0, the upper limit becomes 1 by y, and this thing basically becomes u. And what we have here is dx, du equals to dx by y, or this is du into y. Okay. So what you do have here is follows: 0 to 1 y, 0 to 1 by y, fractional part of u, du. Okay, and dy. So this is basically our integral right now. Now obviously if we were to substitute like that, we would get integral in terms of 1 by y. So if we were to evaluate the inner integral, we would get something like that. Now what we would try to do is as follows: 1 by y is a variable which we would like to evaluate, but we need to find out that since y is less than 1, we see that 1 by y would be greater than 1, right? And what we can evaluate here is the following: 0 to 1 by y, fractional part of u, du. This thing here, this can be written as 0 to 1, fractional part of u, du, plus 1 to 1 by y, fractional part of u, du. Okay. And the thing is, 1 by y as the value of, if we were to just fix the value of y, let us say we can say that 1 by y is less than some integer n. If this were to be true, then what we can do is we can do this 0 to 1 plus 1 to 2 all the way up to so like if 1 by y were to lie in this interval, then we can do it up to n minus 1 to n, and in this whole integration we were to evaluate du, right? And this would give us, in each and every interval, what will happen is, since we know fractional part of u is just u minus box of u, and box of u is just a lower limit, so we will have 0 to 1, and this would be u minus 0 du plus 1 to 2 u minus 1 du, and all the way up to n minus 1 to n u minus n plus 1 du. This would be our resulting expression. Now obviously this expression would be 1 by 2. The next expression would be u minus 1 whole square by 2, which is 1 basically 2 minus 1 whole square, which is 1 by 2 minus 0, which is another 1 by 2. Again we would have something like, let's say 2 to 3 u minus 2, which again would be u minus 2 whole square by 2, and 3, it should again be half, and all the way there would be n halves. So this would basically involve n by 2, where box of 1 by y is basically n minus 1. like this. So what we do understand is that I should be equals to 0 to 1 y into 1 plus. So as we understand that this value is n by 2, and n here is basically fractional part, box of 1 by y plus 1. So it's basically 1 plus box of 1 by y by 2 dy, right? So the first part can be easily evaluated as y dy by 2, and the second part is 0 to 1 y into box of 1 by y by 2 dy. Okay, so the first part gives you y square by 2, basically 1 by 4, and the second part is something a bit more trickier. So 0 to 1 y into box of 1 by y dy. Now box of 1 by y is tricky, so for that what we do is we substitute t equals to 1 by y, and this gives us dt equals to minus dy by y square, or in other words dy should be equals to minus dty square or minus dt by t square. Okay, so therefore I should be equal to 1 by 4 plus this should be 1 by 2, right? This is 1 by 2, and this integral should add the limits from, I guess this minus will turn, this would be infinity, this would be a 1, and the limits minus will turn the limits from 1 to infinity. Y will be 1 by t, box of t will be t, and dy will be dt by t square. So this would be 1 by 4 plus 1 by 2 into 1 to infinity box of t by t cube dt. Okay, so this can be written as 1 by 4 plus 1 by 2. Now you know box of t is basically the lower limit in every consecutive integer interval, so we can write it as sum k equals to 1 to infinity and the integral as k to k plus 1, because as you know the sum of all these integrals would be from 1 to infinity, and inside this integral box of t is basically k, and this is t cube dt. Okay, so it becomes 1 by 4 plus 1 by 2 into summation k equals to 1 to infinity k to k plus 1, and 1 by t cube has an basically k into dt by t cube. So dt by t cube has an antiderivative of minus t square by 2, that is basically minus 1 by 2t square, and this will give you 1 by 4 plus 1 by 2 summation k equals to 1 to infinity k into, now t to the power minus 3 basically is t to the power minus 3 plus 1 by minus 3 plus 1, it's minus 2 there and minus 2 there, so minus 1 by minus 2t square from k to k plus 1. This means it is equals to 1 by 4 plus 1 by 2 summation k equals to 1 to infinity k. Now what you do is you put this lower limit first, which is 1 by 2k square, and you put this limit next, which is 2 into k plus 1 whole square. Okay, so what you do get is 1 by 4 plus 1 by 4 summation k equals to 1 to infinity k, not like this actually, so it would rather be k into 1 by k square minus 1 by k plus 1 whole square. Okay, so 1 by 4 plus 1 by 4 k equals to 1 to infinity, this one will become 1 by k, and this will become k plus 1 minus 1 by k plus 1 whole square. So 1 by 4 plus 1 by 4 summation k equals to 1 to infinity, this will become 1 by k minus 1 by k plus 1 plus 1 by 4 summation k equals to 1 to infinity 1 by k plus 1 whole squared. So the final answer would be 1 by 4. This term is 1, it's a telescopic series, and I'll show you how in in the last part of the video, 1 by 4 plus 1 by 4, and this part is 1 by 4 into zeta of 2 minus 1. So one of the 1 by 4 gets cancelled, and what we are left with is 1 by 4 plus pi square by 24, which is the answer to the problem. So you see that this simple integrals might even be much more integrating that possible. So if you look at the initial integral, it was just 0 to 1, 0 to 1, fractional part of x by y dx dy, and on evaluating we found an answer which is 1 by 4 plus pi square by 24. Completely unexpected, yet true. And for the telescopic series part, let me just give you how to do it. K goes to 1 to infinity, 1 by k minus 1 by k plus 1. So what are the terms of this series? See, the first term of the series is 1 by 1 minus 1 by 2. The next term of the series is 1 by 2 minus 1 by 3. The next term is 1 by 3 minus 1 by 4, and so on. So you see that this series is basically 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 3 minus 1 by 4 plus 1 by 4 minus 1 by 5, and so on. And every term cancels out except for the 1. So the answer is 1. So like this is how we usually deal with series. This is called a telescopic series, where the terms cancel itself out. So anyway, so the answer to the problem would then be 1 by 4 plus pi square by 24. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.